So we're going to get an introduction to cloud native deployment and development. And we're going to do it through the lens of the LoudSwarm platform, which is actually where we're all sitting today. So you should see on my screen right now, I'm sharing architecture diagram, and we're going to walk through a bit of all how this works. We're going to talk about some of the kind of cloud native vocabulary and words that are involved in building a cloud native application. And then we're going to talk about moving from the developer experience into deploying the application along this way, along this path that we're going into. And normally I would be on an Ubuntu desktop. Yes, that is correct, Sean. That is how I normally roll, but I had this all set up on Mac for doing the studio today, so that's what I did. So we need to lay the groundwork for going cloud native. In the previous talk, there was a lot of great discussion about how to, there was some discussion about Dockerizing your application. And that's one of the keys for us, or for me, has been in enabling us to move forward in a cloud native deployment, is being able to deploy an application repeatedly and have the developers think mostly about how can I deploy, not how can I deploy the application, how do I develop new features and increase my velocity of getting new features out the door? And I don't want to think about how it's deployed or scaled. And then the operations engineers on the project want to think about, how do I scale the application? I don't want to care or depend on how do I get all the dependencies deployed and all the inner workings of building these beautiful snowflakes of application servers. I just want to be handed the application. I know what its entry point is going to be. I know what tasks need to run to support the application. And I want to be able to then just deploy that into the cloud and be able to repeat it for each environment where it needs to be deployed to. So for example, into our sandbox environment or our staging environment, and then ultimately into our production environment. And I want to do that on a repeated basis. I want to be able to track what I do in a systematic way of some kind so that I can do this over and over again, day in, day out, and allow the developers to increase their velocity of changes as they increase and develop new features for the application. So that's kind of laying the groundwork for where we're at. The first step was taking an application and being able to containerize those so that we can now onboard new developers quicker. I'll talk about that a little bit, and allow each person to have their own development environment set up however they want, use whatever IDE they want. So if you're on PyCharm, someone's on VS Code, one person wants to develop on VI, I don't care necessarily. But what I do want them to have is a consistent experience so that they're not running into individual problems. But I want that consistent experience, kind of one interface for developers to use so that they can be effective and efficient at coding on their local machine. So how do we do that? For us, it's been moving to using Docker Compose, taking our Django application, where the previous experience would have been a developer installing Postgres, a developer installing Redis, a developer installing Celery and all the Celery tasks and Flower, and installing Mailhog, and installing the Express Node.js server. And if you were to install all these pieces onto your local laptop, that'd be great for one project, but what if you're a consulting company like 6 Feet Up and you're working on 10 projects? Or even if you're not a consulting company, but you're a product company that has microservices, and maybe those microservices have different requirements for different pieces of the application or different application silos themselves. This is where Compose comes in, because I can now specify a specific version of Postgres to run in a container. I can specify specific versions of Redis to run in its own container. And I can give each developer in the code repository that they pull out from Bitbucket, in our case, a Docker Compose file that describes all the moving pieces that need to be installed for them to work on their application, where they only care about Django. They don't care about installing Redis or Postgres, but they want it to work just out of the box. So our developer workflow, and you can go from pulling a clean laptop out of a box brand new. My goal is to get developers to be productive in under an hour. I mean, 40 minutes would be an awesome target, I think, from going from zero into anything installed on that laptop to producing code that can be committed and pushed into production in under an hour. And we can do that with Docker Compose. And we use Docker Compose specifically in the developer experience. We don't use Docker in the deployment experience. And I'll talk about that as we get into the deploy experience of this. But the Docker experience is what really greatly accelerates our ability for developers to be productive right away. So if we look at this, what happens is we have Bitbucket for our source control management. Developers pull code. It has the Docker file. It has the Docker Compose file. It has the Terraform bits in there, which I'll talk about in later, but it's pretty much git clone, Docker Compose up. It pulls all the needed dependent containers and away you go as a developer. And now it sets it up so that you're ready to use, I use PyCharm. So PyCharm is aware of Docker available, allows me to debug into those remote containers. My experience as a developer is set. I'm ready to actually start developing and being productive on my local machine. I'm running the whole stack of software. I didn't set up any of it. The people who need those dependencies in the applications are responsible for setting up. Say I've added Redis caching into my app. I'm responsible for adding Redis to the Docker Compose file so that all the other developers don't have to think about it. When they do a pull and get my changes, they also get my infrastructure pieces that are required to support that code change in the application itself. So that's what's great and works on the developer's experience for getting them to be effective. As developers push code back into the Bitbucket source control repository, we will now start talking about the code pipeline, like getting that code from written on a developer's machine to released into the production environment. And that's where the Bitbucket pipeline comes in. You could do this with GitHub or even strictly in AWS. We mostly are using Bitbucket because that's just one of the tools we've had longer than we probably were doing many more serious development things, or even before AWS had their code commit and kind of code star suite of tools. But we will use the code pipeline and code build from the AWS side as we go to deploy into production. So the Bitbucket pipeline itself is responsible for taking the code the developer has written, building up the image that will be used in production, and then pushing that image into ECR, which is the Elastic Container Registry on the Amazon side. So you see we've gone from Bitbucket pipeline into the Elastic Container Registry. And at this point, it's now AWS takes over, and we are going to be going through a code pipeline and keeping the developers in the loop. So you can see we've got a code pipeline. There's actually a Lambda here that is going to be watching for the pipeline finishing, whether it was successful or whether it was a failure, and pushing that back into our Slack channels. And so I can be basically from my desktop as a developer, I can say we use makefiles too. So that's also part of our workflow. I can say make sandbox release. That will kick off the code pipeline and let me know when it finishes. The code pipeline has many stages set up that basically bring in all the artifacts that are needed, including the image from the image repository. And so now we'll talk a little bit about the LoudSwarm experience. I won't give a demo of LoudSwarm because you're all using LoudSwarm right now, but the front end of LoudSwarm is completely a React application, and it is served statically off of S3 buckets from Amazon. But we build the React application as part of this Bitbucket pipeline, and then the code pipeline is responsible for taking those pieces out of the image that has been built and pushing the static resources over into the S3 bucket that make up the React application itself. You can see that there are deploy tasks that will also happen in Fargate. So we're starting to get closer and closer to the deployment part of this experience. But those deploy tasks will make sure that, for example, with the Django application, you typically have to run a collect static so that it can compile JavaScript and CSS resources to put into a media folder. We also serve those out of an S3 bucket in the media storage. So we have a task specifically set up in Fargate that handles that for us. So we're still using that one image that we built over here in the Bitbucket pipeline, which if you're a developer and wanting to debug a production problem is super nice because you can actually see the exact version of the image that's on production that's maybe exhibiting a bug that you weren't, maybe you didn't catch it early enough in the development process. You can now pull that exact image out of the container repository and bring it back to your desktop and use it in a development environment and actually try and reproduce the bug locally instead of the old way of doing things, which would be, well, jump on a production server and see if I can, debug this thing live. And no one wants to do that. That's where I feel like we've really moved away from these beautiful, unique Snowflake servers into I'm going to package my application into an image. Now, this is where we do need this hitchhiker's guide to cloud native vocabulary. We're talking about images, I'm talking about containers, and I'm talking about Docker. the words get a little mixed up, but basically we want to produce as a part of our build process is the Docker is an image, which is a container compliant, the container engine compliant word, where I'm building the image that will run a container. So think of the image as like a class and the container being an instance of that class. We've got an image that we build, and we can instantiate many versions of that image that are running in live, and those are called containers. The problem is this right here. You'll hear about container registries like Docker Hub or ECR, but they're really image repositories. So if you get confused about that, you're not the only one. Apparently the people who named these things were terrible at it as well, and they couldn't get it right. So we build images that are deployed as containers, but they get stored in a container registry. I'm sorry, but that's just the world we live in at the moment. All right, let's back up before we go into the application deployment part of this. We've kind of prepared our image for production. We're getting ready to, we've containerized our application. We've talked about the developer experience. What we've not talked about is, how did I get all of this stuff built out? And that's where Terraform comes in. For those of you who aren't familiar, Terraform is an infrastructure as code platform for building out infrastructure on any number of clouds. We just happen to be using it here with AWS. But more than using it with AWS, we're also using it with Bitbucket. So we can actually define all of our resources as objects in a Terraform file. Terraform maintains information about the state of what we have deployed, and then allows us to make changes to our infrastructure and visualize or understand what's going to change. So you can see down here, part of this developer experience, we've got the code developers, but we also have our operations developers who are building out the infrastructure we will use. And that infrastructure does include this pipeline, more than just like where we're going to like host our actual LoudSwarm application. It also builds out where we're going to build our LoudSwarm application, kind of a little bit of buildception going on there. But for most part, what you do is, a lot of times, this is kind of the workflow we would typically follow. You may sketch out inside the AWS console or use the Amazon CLI to sketch out the infrastructure you may need for these pieces. And then we'll pull that all down. That's kind of why I've got two arrows here going from CLI and from the AWS console. We'll pull those artifacts all back together once we've gotten a close representation of the end goal and put that into Terraform files. And then from those Terraform files, we can now repeatedly reproduce our infrastructure into, well, in this case, our CodePipeline, but also we will use that same pipeline or the same Terraform to produce our infrastructure for the application delivery. So it does double duty there. So a lot of times Terraform states may start out as a click salad inside of the Amazon console. You may use the Amazon CLI to pull down JSON descriptions of what has been built to help aid in basically transferring that knowledge into a set of files that can now be tracked inside the same code repository as our software development process. And now we can have a full audit trail. We can see what's changed when and where. Also, what is nice here, developers are getting more and more involved in the fact that if they need a piece of infrastructure at some point in production, they can make sure that it gets defined as infrastructure and code earlier on in the process. A way we structure our code repository, we're going to have the Django application of the code, the React application of the code, and the Terraform code all in the same code repository. So any changes we make to the application are going to be atomic across all three aspects there, the front end, the back end, and all the infrastructure. So if my code depends on Redis being present in the sandbox environment, I can, as a developer, add my code that leverages this new piece. I'll add it in the Docker Compose so that the other developers now get Redis installed whenever they do a pull and get my new feature. I will also be responsible for adding it into the infrastructure as code under Terraform so that I can ensure that when my task launches into the Fargate containers, that it'll have a Redis that it can connect to. So it's kind of nice to lock those together so that if you ever did roll back code to, if you were releasing a previous version because you wanted to roll back, maybe do some issue, the infrastructure will follow right along because it's all part of an atomic commit. And if you roll out that one feature, you can roll out the pieces of infrastructure that it was dependent on as well. All right, so Any questions so far? We've kind of talked about building the pipeline. We actually do then now when we want to make changes to this code pipeline, since it's all described in infrastructure as code, it makes it very easy for us to go in to Terraform to identify either new steps in the pipeline or a change to the code build process or some change to those tasks, and then plan and apply that into our environment, as opposed to logging into the AWS console. There's not a lot of, I guess, auditing, other than there is CloudTrail and kind of some auditing level of like who did what in there, but it's really difficult to say roll back to a previous state of the build pipeline. We can always, if someone does go in and clicks around in the console and changes some things, we can always run Terraform now to see what did get changed, and roll that change back out, or incorporate that change back into our Terraform states, and then push that back out as the new standard for what we're using for this part of the build. Right, now let's talk about building blocks for delivery. We've talked about building the application, getting developers all on the same page, leveraging that Dockerized container. Let's talk about where the application the rubber meets the road for delivery of said application. So we're going to slide over here to application delivery. I know everyone loves Amazon architecture charts. I am no exception. I love drawing these things out and kind of piecing together all the various building blocks. And that's one of the core aspects of cloud native delivery for me, is the fact that I can leverage the platform to run, host, and manage some of the kind of auxiliary parts of my application that are not the core pieces of my application. I don't want to manage a Postgres server anymore. I want Amazon to do that. I don't want to manage a cluster of Redis nodes. Amazon could do that for me. I definitely don't want to run email servers. No one on this planet wants to run email servers, and I feel sorry for the people who do have to run email servers, because I ran email servers for ages. No one wants to do that. Luckily, Amazon has, amongst their many TLAs, 3-letter acronyms, has tons and tons of these kinds of building block services that you can piece together to build your application in a robust way that I can now just deploy my container or my image as a container into some server someplace. And I don't even care what that server is anymore, because I'm trying to leverage the serverless aspects of the Amazon ecosystem and infrastructure. That's absolutely true. Even Exchange people don't want to manage email servers anymore, which is kind of crazy. But I want to leverage those building blocks to piece together all the bits and pieces I would normally have to deploy and configure by hand. I mean, in the old way of delivering these kinds of applications, we would have a monolithic server that would be running postfix to send mail. It'd be running Varnish to cache our content. It would be running HA proxy to do some kind of load balancing. And then I'd be responsible for running my own, WSGI server with Django and all the instances of Django that I would need together. Being able to do this with now containers and Docker Compose, and then actually moving from Docker Compose into this infrastructure where I'm actually using Fargate. So we'll kind of start down here in the private subnet area, the application delivery of this. These are Fargate instances, well, it's tasks that have been deployed as containers. And we deploy different containers for different styles of workflows here. Technically, I believe, yes, technically these are all using the same image, but they're being deployed with different entry points so that they can service different types of tasks. For example, the Django task here, if you've looked at the LoudSwarm application, you'll notice that it's all being served out of these S3 buckets for the React application and for any static assets that are inside the application. Everything else is going to be API calls back to Django. Django does no rendering of any server-side pages that are delivered to you as a user of the LoudSwarm platform. Those are all API calls. And so the API calls can be somewhat compute intensive depending on what they are. And we'll talk about how we've gotten around that and how we discovered where there were problems. As opposed to, if you notice when you're using the LoudSwarm application, there is a Slack box on the screen where you can see, track 3 cloud. You can see, actually watch the discussion going by in real time. Those are using WebSockets. And WebSockets are very different than the REST API calls. And the REST API calls are typically stateless, just like HTTP, but WebSockets are stateful. They establish a stateful, long-running connection between your browser, so the event attendee up here, and the application itself, so that I can send new messages that come in over Slack through the event webhooks back out to all the attendees who are connected and watching this session live. The type of work is very different than the stateless API calls. The WebSockets requires some amount of RAM per attendee who's watching, and I need to be able to scale that differently than I need to scale the APIs. So even though I'm using the same container image, I'm using them in different ways. In this case, the WebSockets, any WebSockets coming in are being split out to a different backend from the ALB. So that's our load balancer, and going into the WebSockets containers, which can now scale separately from the Django REST API containers. So the key bit there is we can now use the auto scaling groups and set up different scaling characteristics based on different parts of our application. Even though it's all the same application, this part is handling traffic in a very different way than the REST APIs. Same is true for the asynchronous task runners back here. So the Celery workers and Flower, which is a management tool for watching those asynchronous tasks. There are periodic tasks that run in the background on a time schedule or in response to something happening via the API applications. We don't want those to slow down the API responses to the application. They can be done in the background and then possibly sent back over the WebSockets to the end users. We can now scale out tasks. So if we have an event that's 500 people, or if we have an event that's like 5,000 or 50,000 people, we can run a different number of workers to make sure that the tasks don't backlog and get kind of stuck. And that also frees up, again, the ultimate goal here is free up the number of requests that the Django service itself has to deal with, so it can very quickly respond to the application and make sure that everyone has a good experience when they're watching LoudSwarm demos here. So I mentioned performance. Now, one thing I want to mention about performance is tools like Sentry, and I think I mentioned this during the last talk in track 1, are awesome. They recently added in some performance tracking tools. They allow you to do some amount of tracing. There was some discussion about open telemetry in track 1 as well, but we've been using Sentry for a few years now, and they recently added in performance tracking to the Sentry monitoring bit. So normally it was like error tracking. I could see like when an exception happened in my backend, I'd be able to go in and trace down, see the call stack and the database queries and see what's going on. They have something similar now for performance. So as leading up to our early events in the LoudSwarm's lifetime, I highly recommend folks do load testing against your applications. We found that as a developer sitting on your own machine and basically clicking away at the application itself, you aren't going to run into some of those edge cases where if you had 100 concurrent users or 1,000 concurrent users hitting the application, you get a very different load on your machine, because maybe you were doing some things that were inefficient or seeing lots of queries. But as a solo user on your own dedicated workstation, you're not going to uncover those until it goes into a bigger environment where you're using some load testing to actually identify those issues. We had an issue, and this is something everyone should kind of be aware of when they're developing applications, of at the top of the hour, you'll notice our schedules all kind of run top of the hour is when new sessions start. Our React application was reloading the player on the page and doubling up the number of requests that were coming in for the new player and the new session metadata, and just killing our performance, kind of a thundering herd. We inflicted this upon ourselves. So you have to think about how you re-architect your applications to handle queries like this. So for example, the bar along the top of the LoudSwarm application where it shows all the drop-downs with the various sessions that are in them, that was many different queries, which we've now optimized to be a couple queries. But the problem was on the backside, the REST API was actually querying the database for that same data all at the same time. So if you had 200 users all querying the database for this very large and kind of time-intensive query, the server was falling over. Now, another kind of pro tip in here: auto scaling can only get you so much. If you are auto scaling and you have an auto scaling group set up and you've got it set for, if my container runs at 80% CPU for some amount of time, start spawning new containers to handle the additional load. But if all the load comes instantly into your application, and you don't have enough containers already available to handle it, those containers most likely will start falling over. Either they're running out of memory or they're going to get bound in some way, CPU bound, IO bound, memory bound. Those are kind of the main things to start looking for. We had that exact problem. That at the top of the hour, our existing containers that were hosting the application would fall over. The autoscaler would see that they'd fell over and start spinning up more, but they were starting to get bogged down with requests before they could even get spun up in time to start servicing the requests. So you have to look at how you can use the autoscaler smart and make sure you like pre-warm some instances, or if you have to be able to anticipate what your application's traffic is going to be like. And that's going to be different for every application that gets deployed onto any service, no matter what. But if we step back, this is where effective caching comes in. We are using CloudFront as a CDN as part of our delivery pipeline, which is nice, having a content distribution network that has over 200 points of presence across the globe. That means that everyone who uses our application gets a pretty reasonably nice and snappy experience, because typically the resources they are looking for that build up the application are going to be right next to them. Same thing for our video CDN. All the web content, all the video content you see inside of the application is being streamed live from Zoom and being streamed into our video CDN, and that's also being redistributed closer to the attendees. So we can make sure that folks who are all the way across the other side of the globe get a relatively similar experience to someone who's sitting here in the United States of America. So that's great for caching of the content, but we also needed to cache some of the queries. Like some of the queries are more expensive. Like for example, generating the whole schedule for a specific event can be a pretty expensive operation, especially if it's being hit multiple times, almost instantaneously. So originally we had set up that the schedule could be cached into Redis. So we use Redis cache to build up, we do the query, build up the result set, cache it into Redis, put a TTL on that, so time to live for that data. And if the application sees that there is a cache version of the schedule data, they will serve it up. If there isn't, if the TTL is passed, then the query will happen again. So that person may get a bit of a lag as they wait for that query to complete and actually serve them the result of that expensive query. Taking that the next step further, we now set up some task workers in the background because we know that query is going to happen. The schedule doesn't change that often. So instead of having a 3-minute or 5-minute TTL where someone might get stale query data and also have to suffer the performance penalty of waiting for that REST API to regenerate the content, we can now pre-generate that content, throw it into the Redis once a minute with the same TTL just in case. So in case that generation would fail somewhere along the line, the TTL can still kick in and content can still be generated on the backside, even though there might be a delay. But now everyone gets the snappy experience of getting basically all of the API, the majority of the expensive API calls inside of our platform are going to be delivered straight from Redis because they've been pre-calculated and are ready to go, which greatly reduces the amount of load and the number of containers you would need to actually serve this application in the real world. Now, we do want to monitor things. And so we use CloudWatch for monitoring inside of AWS. So we can see, for example, the flower process. If we want to be alerted to the fact that maybe one of those tasks that was generating our schedule didn't succeed, we can now get alerted by watching Flower for long-running tasks or failed tasks and have that kick off a Lambda, which can now then go notify us. Which also means we don't have to run that infrastructure for logging. As long as you're following some of the best practices from a 12-factor application, we log the standard out, and all of our containers are doing the same kind of way of logging. All those logs now get shifted over into a single spot where we can actually easily query them using CloudWatch metrics. We also are able to use CloudWatch metrics with their new dashboards to watch general health of the whole application. So we can actually see and put in place some critical, I'm going to say it, single pane of glass type metrics, where we can now watch the health of the application, hopefully anticipating if there's going to be any issues. Now we know, basically how we need to scale the application in anticipation of larger events versus smaller events, and we can scale back down to almost nothing in between times when there's not any events running. So we're not spending money running a giant server like we used to in the old days because we needed to have that capacity ready at a moment's notice. We can now leverage the elasticity of the the Elastic Cloud to handle that for us. And we also have incorporated some other services that are part of this stack. You can see Route 53, SES, which is the mail service. This is our CloudWatch dashboards. This is guard duty, literally a checkbox to throw into the mix for CloudFront. We get the benefit of adding a web application firewall to CloudFront. So for those of you who aren't familiar with web application firewalls, you can now, I did say it, Chris, and I did drink. We can now have CloudFront evaluate the traffic that's incoming, looking for malicious traffic, and deny that traffic even getting into our application space at all. So before it even gets to hit the ALB or anywhere near the Django application, that web application firewall can watch for some really kind of easy, well-known exploits. There's some awesome examples of using that web application firewall where you can actually put into it some smarts, like run some lambdas, have some analysis done against the traffic, kind of trying to anticipate or forecast malicious traffic coming into the site or things that are anomalous to your site. And one of the other pieces that I haven't talked a lot about is secrets management as part of your web application. Nowhere in here have I talked about secrets, database passwords, tokens and credentials. That actually, some people hopefully don't put it into your infrastructure as code. What we do for our secrets management is Terraform will deploy, but it'll have references to the AWS SSM parameter store. So the parameter store, that's the fancy icon right here, allows us to securely store our secrets for each environment. So sandbox, staging, and production in a secure fashion that is available to the application or to specific people based on their IAM role in the cloud infrastructure. So what's nice here is we can actually say that developers could have access to, say, the dev environment or the sandbox environment credentials, but we don't have to give them access to those credentials in the production environment. Things like the Django secret key, because we will use encrypted fields, for example, inside the application. That encrypted key is only available in the parameter store for production. And it's only and then we can give roles to these various containers that allow them access to grab those keys as they spin up. We use environment variables for passing in all the credentials, keys, secrets, you name it, because we have numerous ones of those. There are going to be secrets for Sentry, there's secrets for talking to Slack, there are secrets for the database, there are credentials or secrets such as the Django secret, and we don't want those in plain text anywhere. Not anywhere. The developers will have dummy versions of that inside the Docker Compose file, and each developer can change those as they see fit. But that way, there's never secrets checked into source control. There's never secrets checked in with Terraform, and we can actually still manage that and key and rotate the secrets as needed using the parameter store. And then as new instances spin up, they will grab out the latest versions of those secrets. So that is kind of the using environment variables and keeping secrets secret. One thing I didn't talk about yet was we have a single URL that accesses the application. And so everyone comes in through the front door of CloudFront. CloudFront is a really nice tool to throw in front of almost any application. You can host static websites in S3, put them in front of CloudFront, or you can use EC2, or in our case, we're using Fargate containers. One other thing, so I'll reverse back up real quick. One other thing I forgot to mention was our Django container, all these containers that are running down here are using the Fargate service, which means I am not managing an EC2 instance that is running our containers. I'm also not managing a Kubernetes cluster, which as soon as you invoke that word, a giant stack of management tools and complexity all of a sudden appears in front of you, like as if you were playing a D&D game and had gone down into a dungeon. No one wants that. I'm trying to keep this whole architecture as simple as it needs to be and no more complex until there's a requirement for that complexity to be introduced. The simpler and the less lines of code means hopefully less surface area and less bugs, but it also means that it's approachable by us mere mortal developers. If you design a system that is so complex that you cannot debug it, is obviously not a good system to maintain in the long run. So I like to recommend to folks to keep things as simple as possible and just until they just can't stay that simple. So not having to manage EC2 instances is also a benefit because I'm not dealing with that. I just specify in our Terraform what size containers, whether I need more CPU, whether I need more memory, whether I need really small ones that can run many at a time, to scale horizontally, That's all done in Terraform. I'm not managing or owning any servers. I only pay for when those instances are running. It's kind of a best of all worlds there, in my opinion. Now, no one can access any of these containers. There's no shell on these containers, which is also another big benefit. There's no way to SSH into those containers, and there's no public access to those containers. You have to go into the front door. You need to enter the site through the load balancers. Even the database is not accessible publicly, which I don't know why people do that, but some people do. That's why we have a management VLAN over here, or VPC over here, where in case I do need to get a database dump, off to someplace, I can't do it from the application because there's not a shell to log into. But I have put together, or we do have like a Bastion host where we can now go and grab a database dump of the data if we needed. In that same management VPC, that's also where the ECR repository lives for our containers. So that because each environment will need to have access to the container to pull them and then deploy them into the environment. Each environment has its own, I should have mentioned that too. Each environment has its own code pipeline, code build, and deployment process. So you can actually move changes for your pipeline along, just like you move changes for your code along as well. So if I'm changing something about the code pipeline, I want to try that out in the sandbox environment first. No one wants to have that accidentally slip into production. And those are managed on a per environment basis. But the images themselves are a fairly global artifact to the whole application, so that we can make sure that each environment can pull whatever specific version of the image. Every image is exactly the same across sandbox, staging, and production. The only thing that changes is going to be the secrets that are passed into it as environment variables, or configurations are passed into it as environment variables. The code stays the same. The containers themselves are immutable. Nothing is written into the container. All the logging goes into CloudWatch. All the parameters come in as from a parameter store or from as environment variables, so that I can ensure that no code changes. When I'm sure I've got an image that works in Sandbox, I can deploy that image in production. If I have problems in production, I can pull it to my local machine and now debug as appropriate. Okay, the last bit I want to talk about, because I got a couple more minutes left, is load testing. I mentioned we caught some early issues with load testing. The tool we use for our load testing, and I highly recommend it, is Locust, which is also written in Python. It's an asynchronous load balancing tool that allows us to put together more realistic real-world application load against our system. Now, you have to be careful when developing load testing for your applications. You want to avoid kind of hotspots in the application. As an example, if you want to simulate 1,000 users logging into your site simultaneously or across some time frame and doing some kind of actions inside the site, you'll want to be careful that you aren't using the exact same user to log into the site. Because, for example, you may write out a last login time, or you may use that same last login time. Well, if the same user is logging in simultaneously across 1,000 instances, you may see strange hotspots in your database that aren't actually mimicking real-world performance issues, and you may miss other ones because maybe data is getting cached for that specific user and just being sent back out 1,000 times. So Locust allows us to actually build up and feed it a kind of a fixture full of 1,000 different random users. So we have a utility built into the application that can allow us in Sandbox to generate n number of random dummy users for our load testing test cases, and then we take that same spreadsheet of users and pass it into our Locust cluster that is going to be doing the load testing against the server. So we can now see real world load testing. We take that load, the Locust allows you to write a Locust file, you pass that in, you can specify task groups or sets of actions that are happening together. So if you want to simulate someone viewing the schedule, clicking on a session, clicking back to the schedule, or you want to simulate the whole login process, or another nice thing about Locust that you can't do with a lot of other tools, not only can we simulate the API calls, hitting Django and requesting all the resources and the data, we can also simulate the webhooks. We wanted to make sure we had enough resources available for the WebSockets, not webhooks, for the WebSockets, to ensure we didn't run out of memory. The kind of main constraint for WebSockets on the server side is going to be memory, because each connection back requires some number, kilobytes to megabytes of memory. We want to test that. And so with Locust, I can have 1,000 different users establish 1,000 different WebSocket sessions. And now I can see how that application is going to balance those WebSockets across multiple containers running and try and hopefully identify any of the bottlenecks or edge cases when they've got maybe that much contention for sending across the WebSockets channels. So I make sure you kind of lay out and think through how you're going to test and debug with Locust. Also, debugging remote tests like that, or debugging a Locust load test, is kind of tricky because the code runs asynchronously, but it's not impossible. Python has some awesome tools for doing that, like the remote PDB. So we can actually dig into a load test as it's running, spawn a remote PDB, maybe at either an exception or at a breakpoint that we put into the code. And now we can actively with PyCharm or PDB, analyze and see, is it a specific user that's being reused, or is there some kind of error in our test methodology? That was a huge help in actually making sure this all went smoothly. With that all being said, I want to thank you all for hanging out with me for the last 45 minutes and chatting about Terraform and Terraform and Fargate and deploying applications. And I hope you really enjoyed seeing kind of a meta presentation about the platform you're actually using right here to watch LoudSwarm. Thank you all so much. I will be wrapping up and jumping into the face-to-face meeting. So if you want to talk to me, click on the link down below. I will jump into face-to-face for a few minutes before I need to go back over and moderate my track number 1. Thank you all for joining. I will be around the conference all week long, and I love chit-chatting about cloud native deployments. And I look forward to talking to you all. Thank you for coming out and seeing me.